This is chapter 20, which is going to cover acids and bases, and we're going to start at the very beginning, what makes something an acid, what makes something a base, go through some different theories, and then we'll get into pH and all of the other things that go with it. So to begin, let's talk about just some general properties. These are things that you probably already know, like acids taste sour, they're found in citrus, they turn blue, litmus red. They also react with some metals to produce hydrogen. That's one way that hydrogen gas is produced to use in a lab. And then bases generally taste bitter, they feel slippery like soap, and they turn red, litmus blue. And we're going to be exploring some of those properties a little bit more in one of our labs. Okay, so to begin with, we need to learn how to name an acid because the acids have different rules for naming than just plain ionic compounds do. So we need to look at these rules, and we're going to practice these a lot more in class. All right, so to begin with, acids are ionic compounds, but instead of the cation being a metal, the cation is a hydrogen ion. That's how you're going to identify an acid, is because it has that H plus as the cation. And the name of the acid is based on the name of the anion. So here are three rules. First, when the anion name ends in "ide", like chloride, bromide, sulfide, the acid name begins with hydro and ends in "ic". So you're going to take off the "ide" and replace it with "ic" and have a prefix of hydro. When the anion name ends in "ate", like nitrate, sulfate, phosphate, the acid name is going to end with "ic", so we replace the "ate" with "ic". And when the anion name ends in "ite", like sulfite, nitrite, chlorite, the acid name will end with "us", so we replace the "ite" with "us". Now these rules only apply to acids. Bases are just named like normal ionic compounds. There are no special rules for bases. So we're going to work on these examples in class, so we're going to skip this slide for right now. Okay, let's talk about what makes a solution acidic or basic. Now, acidic and basic solutions are just that. They're solutions. They're aqueous. They're dissolved in water. And all solutions that are dissolved in water contain hydrogen ions, which is H+, and hydroxide ions, which are OH-. The relative amounts of the two ions help us determine if a solution is acidic, basic, or neutral. So an acidic solution contains more hydrogen than hydroxide ions, and a basic solution is the opposite, contains more hydroxide than hydrogen ions. In a neutral solution, like just plain old water, there are equal numbers of both ions, hydrogen and hydroxide. And when we get to pH, we're going to be giving a value to how much hydrogen or hydroxide is in a solution. Okay, so let's talk about water to begin with, since these things are dissolved in water. Pure water by itself actually produces equal numbers of H+ and OH-. This is called the self-ionization of water. And what happens is two water molecules, if they have enough energy when they bump into each other, they're actually going to switch a hydrogen. They're going to move one hydrogen to the other water. And so we're going to end up with H3O+ and OH-. So one of them is losing a hydrogen ion and giving it to the other. So we end up with both of these ions just a little bit in pure water. It doesn't do it a lot, but it does it some. Now, the H3O+ is called hydronium. And it's actually the same thing as H+. We don't always use the water that the hydrogen is attached to. Sometimes we leave the water part out. So we can say that a hydronium ion, H3O+, and a hydrogen ion, which is H+, we can say that those two things are equal to each other, or they're interchangeable with each other. Okay? All right, now, how does a solution become acidic or basic? Well, there are two different theories we're going to look at. The Arrhenius theory is the very first theory. It was the first kind of idea of how something became acidic or basic. And Arrhenius said that an acid is a substance that contains hydrogen and produces hydrogen ions when dissolved in water. And a base is a substance that contains hydroxide and produces hydroxide ions when dissolved in water. So as you can see, they both have to be solutions. They're both dissolved in water. It just depends on when those things dissolve, what types of ions are being given off, just like we saw in the solutions chapter. When ionic things dissolve, they break apart into ions. If one of them happens to be a hydrogen ion, then it becomes an acid. If one of them is a hydroxide ion, then it becomes a base. So you can see here, when hydrogen chloride dissolves in water, we get hydrogen ions and chloride ions, so that's considered an acid. When sodium hydroxide dissolves in water, we get sodium ions and hydroxide ions, so that would be considered a base. Now the problem with the Arrhenius theory is it's very narrow. It leaves out several substances that are basic when they're in water, but they don't necessarily have hydroxide in them. And so we're going to get to the next theory in just a second. But when we're looking at Arrhenius acids specifically, we have to look at what are called ionizable hydrogens. Which hydrogen ions are actually going to turn into ions when they dissolve? If a hydrogen is bonded to something that's very electronegative, like fluorine or oxygen or nitrogen, then it's ionizable. It can become a cation in solution. And if an acid has one ionizable hydrogen, then we call that monoprotic. Now this term protic comes from the idea that a hydrogen ion is just a proton. Hydrogen as an atom has one electron and one proton. So when it's lost its electron to become an ion, it's actually just a proton. That's all that's left. So a hydrogen ion can be called a proton. So the term monoprotic means one proton or one hydrogen ion. 2 ionizable hydrogens is called diprotic. 3 is called triprotic. You might also see the term polyprotic, meaning more than one ionizable hydrogen. So for example, when we look at acetic acid is HC2H3O2. It has 4 hydrogens in it, but it's monoprotic. Okay, so when we look at the formula for acetic acid right here, we can see that 3 of the hydrogens are attached to carbon. Carbon's not very electronegative. 1 hydrogen is attached to oxygen, which is electronegative. So this hydrogen is the one that's going to break off and become a hydrogen ion. That's what makes acetic acid monoprotic. These other hydrogens that are attached to carbon are going to stay attached to carbon. So in the formula, this hydrogen that's separate from the other 3 is the one that becomes the hydrogen ion. Okay, let's talk about the Bronsted-Lowry theory. This is the more updated version of what acids and bases are. And the definition of an acid is a hydrogen ion donor. A base is a hydrogen ion acceptor. So for bases, it doesn't have anything to do with having hydroxides. It has to do with accepting a hydrogen ion from something else. So let's look at our 2 examples. Here we have HCl and water produces the chloride ion and the hydronium ion. So we can see that HCl donated a hydrogen to water. So that makes HCl an acid, according to Bronsted. Okay. Now on this one we have NH3 plus water yields NH4 plus hydroxide. Now here the NH3 actually accepted a hydrogen ion from the water, so the NH3 is a base. Now you can see that it's a base because we still end up with hydroxide even though the NH3 didn't have it to begin with. Okay. So acids are hydrogen ion donors. Bases are hydrogen ion acceptors. Now let's talk about what we get when hydrogen ions are donated or accepted. The products are called the conjugate acids or the conjugate bases. The conjugate acid is the species produced when a base accepts a hydrogen ion, and the conjugate base is the species that results when an acid donates a hydrogen ion. Now these are the same 2 examples we saw previously, and we know that we said the HCl was the acid and the NH3 was the base. Now here in this example, what is the water doing? Well, as you can see, the water is actually accepting the hydrogen from the HCl. So in this particular case, water is acting like a base. It's accepting a hydrogen ion. So in our products, the chloride is what's what results when the hydrochloric acid donates the hydrogen. So we're going to call the Cl- the conjugate base, and the H3O plus is the conjugate acid. Okay. Now down here, the water is what donated the hydrogen. So in this case, it's actually acting like an acid. And then in our products, the NH4 is the conjugate acid, and the OH minus is the conjugate base. And we will practice more of this labeling in class. Now I want you to pay attention to one thing. Water can be a base. Water can also be an acid. It has hydrogens that it can donate, but it can also accept them. And we call that amphoteric, something that can be both acidic or basic. Water is an amphoteric substance. There are others, but water is the most common one that can be both acidic or basic. It can both donate or accept hydrogen ions.